Hi, um, welcome. In this lesson, we are going to be covering logistic regression, and that's going to be um, a dive into, like we did for linear regression, it's going to be a dive into the idea behind logistic regression, which we are going to be looking into, and then we are going to be taking a simple data set, and we're going to try to train a logistic regression model using that simple data set. Now, what is logistic regression? So in the last class we looked at linear regression, and we tried to like understand the idea behind it, how it works, and what happens under the hood. Now let's actually see logistic regression. So now logistic regression is, although it is called logistic regression, it is actually a classification problem. And from our introduction to machine learning, we learned that um, classification problems are those ones where you expect to have you have your target, not expect to have, you have your target as categorical variables. For example, let's say I have some x1, x2, and I have some y. And in this case, my y is some categorical variable, let's say 10001. Then I have some 2, 4, 3, 1, 2, 6, 4, 1, something like this. So I have some values of x's, and I want to predict some y's. And in this case, the y are not um like what we had with a regression problem where they are continuous variables. So in this case, they are categorical variables, and this is a case of binary classification where they are just two different classes. So these ones and zeros could be anything, could be yes or no, has cancer, does not have cancer, approved, rejected, anything like that. Now, but classification algorithms can not only be used to model binary classification data sets, so you can have multi-class classification also. All right. So how does that work? So in logistic regression, the whole thing that happens is basically almost the exact thing that happens in linear regression, except for a tiny difference. So what happens whenever we are training a logistic regression model? What actually happens is we are also doing the normal y equals beta naught plus beta one x1 plus plus beta two x2. So we really should call, instead of calling it y, let's call it something else. Maybe call it z. Now we are actually, this is going to be our prediction, right? And it is the same thing that we had when we were working with linear regression. But here's the thing. Now imagine this y, this y that we have. If we are to plot this y, let's say it is two-dimensional. For that here, let's say y is two-dimensional. That is, there's just like one, just a pure relationship between x, let's say x1 and y. I'm just saying. So it means that these are x1 and this is our y here. That means on y axis there are just going to be two things, and let's say this is 0 and this point here is 1. Then we have up to 4, so we have x is 1, 2, 3, and 4. Now, for the first one, when x1 was equals to 2, y was equals to 1. So when x1 was equals to 2, y was equals to 1. So at this point, let me just get a different one to like make it very obvious. So when x1 was equals to 2, yeah, y was equals to 1. So around here. Then the second one, when x1 was equals to 1, this guy was 0. The next one, when it was equals to 2, 0 also. When it was equals to 4, let's say that is 1. When it was equals to 4, that is 1. So, we could have more. We have 5 things here. Maybe we could squeeze something somewhere in here, right? But that is on the go, right? Now, what you are going to find is that for everything that um we are going to have in terms of the y, it is either they are lined up here on this line, or they are lined up here on this line of zero, because we only have zeros and one. Now that presents us with a little problem if this is everything we are using to model, because this particular equation here, this equation will fit a straight line like this to our data set, right? And that is not what we want to do, because if we fit a straight line like this, imagine we have more data points like this, let's say something like this, and we also have like this, then we have a problem because majority of the points are missed. We've missed a lot, majority of the point. And that does not mean the result from this output is not correct, or it does not have some nice information. It does. But it is just that it does not fit properly to the reality of what is inside this place. So that is where something called sigmoid function now comes in. That is where sigmoid function comes in. So the next step is to actually convert this to values of zeros and one, which is going to like you know look like what we have in the real data set. So in the real y. So how do we do that? We use something called sigmoid function. And how does that work? So we can call that, you can say sigmoid is going to be equals to, that's going to be 1 all over 1 plus exponential minus z, which is this z that we have here, right? This z that we have here is what we see here. So what does that mean? It means we solve for y using this our normal formula or whatever we want to use to get our regression one. And once we have the solution of our beta naught, beta one, all of that, we plug that into this and estimate a new value for z. And once we have that new value for z, which is going to be some continuous value, some numbers, what we do is we plug it into this particular equation, and it is going to return a value that is between, well, it's going to be between, so the answer, the return of this is going to be between 0 and 1. So, and in that vein, anything that is less than 0.5, let's say this is the 0.5 mark. So anything that is below 0.5 is going to be classified as, zeros. And anything that is above 0.5 to 1 is going to be classified as 1. And that's basically how what do you call it, logistic regression, how it happens. That is what happens. Firstly, we get our z, which is going to be a normal output of a regression. We compute a normal regression output, and once we have that, since that's going to return a continuous variable, and that is not going to reflect what we have, we are going to turn that to a sigmoid using the sigmoid function. And when we apply that sigmoid function, what do we expect? What are we going to get as output? We are going to get something that looks like this. Perfect. So we are going to get something like that looks like this S, that actually properly model our data set. And that is just basically what um, logistic regression, the steps for logistic regression, right? So let's get into how to write something like that with a simple data set. like I said in the last class, the focus of this is to actually show you logistic regression, teach you logistic regression. It is not a class on it's not a session on exploratory data analysis and all of that. And like I have said over and over again, the most important aspect of ML really is actually exploratory data analysis. So, but the focus of this particular video is to teach you logistic regression. So we are not going to be doing a lot of EDAs. We are not even going to be doing EDA as much. So let's get into it. What do we need? First, let's connect this. And the next thing to do is going to be to import all of the libraries. As usual, the first one we need is pandas. Let's import pandas as PD. I'm going to import numpy as NP. I'm going to say from sklearn dot linear model. From sklearn dot linear model, we are going to import. Let's try and connect this. From sklearn dot linear model, we're going to import logistic regression. Then we're going to say from SQL. So the data that we're going to be using is going to be coming from data sets from sklearn. Data set that we're going to be using is going to be coming from sklearn. It's going to be practice data set from sklearn. We're going to say from sklearn dot data sets. Yeah, we're going to import load underscore breast cancer. So we're going to be using this breast cancer data set. Then I am going to run that, and that worked. So the next thing we will do, let's add comment here and say load the needed libraries. So the next thing we'll do is to actually set up the data set. And we're going to say x is going to be equals to, and the way data set from this load breast cancer work is this. So let me just show it to you. I say load underscore breast cancer like this, and I run that, I'm going to get a dictionary of data, which is going to be the X and the Y. So I'm going to have a dictionary that has two keys. And first key is the data, which is basically the X's, the features. And the other key is going to be the target, which is going to be the Y's. And I can also say as frame equals true. That is, I want this guy to load as data frame. So you're going to see that we have something like that. But then I don't see you're seeing some form of it, right? This is not the non-binary anymore, it's loading as the pandas data frame. But what we're going to do is we're going to actually select this particular key so that we can only point to the axis. So if you should run that, that is still loading, loading, and it should be here now. So we're going to these are our axis. All of this we want to use it to predict the y's. So I can come here and say x equals this. Then I can come here and say y equals load underscore breast cancer. Essentially the same thing as underscore frame. We don't need, that's not important. Just say target, right? Target. Great. So give me a minute, let me forget this. My collab is not okay. I think we are back up. So we run that, we are good. Great. So we've set up the data set. So if you do x.add like this, you should have an output like this. So this data set is fairly the only thing we might need to do is just scale it, because right there are like all of these different scales. So we might need to to scale it. So I'm going to come here, and you've seen a few of these in the class on linear regression. Let me say from Sklearn dot preprocessing import. Let's use robust scalar from Sklearn dot preprocessing import robust scalar. Um, then we also need to import um, we need to import train test split. My internet is misbehaving, so let's do from sklearn dot model selection. I need to import train test split. Then we run that also, and we are good. So I'm going to come here and scale the data set all over. Let me show you what the y looks like so that you see. So these are our y, just zeros and ones, zeros and ones. These are the things that we are trying to predict for each of these guys. So this first line here, this first line, this first record correlates with this zero prediction. The next one, like that, like that. So we are going to scale. How do we do that? We're going to say scalar is equal to robust scalar. And we can come here and say column so that we can return that back to the pandas data frame later. So say column equals x dot column equals x dot columns, and we're going to say scalar dot fit. And what are we fitting? And we're going to be fitting x train. So this is how we know that we should firstly, it's good practice that you scale first and that you split your data set before scaling it so that you don't leak information in your training data into the test data. So let us firstly split. So I'm going to split the data set. We're going to say x underscore train, x underscore test, y underscore train, y underscore test equals train test split x comma y comma test size, and that is going to be 0.2. We are taking 20% as the test set. Then we set random state so that we can always be able to reproduce this exact split. The last thing we are going to pass in is stratify, so that I'm going to give you stratify equals to y, so that um you know the way it samples this thing, the way it splits this thing, does it with respect to the distribution of y, so that the number of things we have, if we have class imbalance, it is not going to just choose one side and miss the other side. That it is going to split this thing with respect to how the data in y is distributed. So if we run this, we are good. So we can come here and say x underscore train equals scalar dot transform x underscore train. Then x underscore test equals scalar dot transform x underscore test. Then we can convert both back to pandas data frame. And how are we going to do that? We're going to say x underscore train equals pd dot data frame and x underscore train columns equals columns. And we can do the same thing for x underscore test. That's going to be pd dot data frame and x underscore test. columns equals columns. Right. Okay, that's cool. Let's just add S here. So if we run that, the scaling is done, and we've also done our split. The next thing that we move on to is the model training. Let's train the model, and this is the part where we actually do what we have here. We do all of this modeling and stuff. But like I always say, Sklearn has already done majority of the heavy lifting for us by giving us this particular class here, this logistic regression class. So all we have to do is come and say model equals logistic regression. Then we're going to say model dot fit x underscore train y underscore train. Then we're going to say train underscore prediction is going to be equals to model dot predict x train. Then test underscore prediction is going to be model dot predict x test. And we can run that. And then the last thing we're going to do, just like we did in the last class, is evaluation. In the regression classes, we're going to evaluate the model performance. And for regression problems, I told you that one of my go-to, which is one of the most popular metrics for evaluating, is RMSE. But the same is not the case um for classification problems. So there are some there are some there are some metrics that we use to evaluate um classification problems. And these metrics, I'm trying to bring up the board here. Okay. These metrics are accuracy, F1 score, precision, recall. So we're going to have a look at each of them right now. So let's start with, let me demarcate this place. Great. So let's start with the first one, which is going to be accuracy, which I'm guessing is something that we have heard before at some point. Right. So now, like I said earlier, there are a few metrics. Number one is accuracy. Nobody uses this as much. And accuracy is going to be the ratio of all of the correct predictions. So that's going to be correct predictions, correct predictions all over total prediction. So that is accuracy for you, correct prediction all over total prediction. So if we have like you know 10 things to predict, how many of it did we get right? So the reason why accuracy is not does not make so much sense is, let's say we have our y true. We are trying to predict between cat and dog. Let's say that's what we're trying to do. We have a model that can predict if we are looking at the cat or we are looking at a dog, and we have the true things that happen. So let's say y true, we'll put that here, and that is going to be equals to, so let's say it is a list, and this list is going to be cat. Let's say, let me come here and say cat is going to be equals to 0, dog is going to be equals to 1, right? So for our first one here, we are going to say 0, 1, 1, 0, 1, 0, 0. That's how many? That is 1, 2, 3, 4, 5, 6, 7. Let's do 1, 0, 0. Great. We have how many ones? 1, 2, 3, 4, and we have six zeros. Great. So we have six dogs, six cats. Don't forget, cat is 0, dog is 1. Now let's say we've trained a model, and this model is expected to make predictions. So y pret is now. So what happens is every time, this, let's say this is a very dumb model and it doesn't have the capacity to even predict that something is a dog. So everything is just saying everything is cat. So 0, 0, 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Great. Now, if you look at this particular scenario here, we have the true prediction that happened, what really happened, which is all of this. And we have what this model is predicting. This model is predicting it's saying that every single animal, which in reality we have six cats and one and four dogs. But in this case, it's saying everything, they are all cats. Now, what's the accuracy of this? The accuracy of this is actually how many did it get correctly? Right? How many of these did it get correctly? Well, it's going to get six of them correctly because it's saying everybody is cat. And for real, we have how many cats? Six cats. One, two, three, four, five, six. So that would mean the accuracy for this is going to be accuracy is going to be 6/10, which is going to be 60%. So this guy is saying this model, which actually is a dumb model, it is saying that it is 60% correct. Now imagine by chance, or everything we have in white is about nine cats and one dog. We are going to be attributing this brilliance to a very dumb model, and we're going to say, oh, this model is 90% accurate, which is not true. And that is how um, accuracy misleads us. So that's what actually lead us to evaluating and trying to check out some other metrics that are, way better than accuracy. And some of those is number one is precision. Then precision is actually uh, the the true positives, the ratio of true positives. So true positives all over all positive prediction. That is precision. So out of let's say we are checking for the precision of cat. So we are saying how many cats did it actually get correctly? How many cats, how many real cats did the model predicted to be cats? That is this value here. All over how many predictions did the model actually say are cats? All of the cat prediction. So this one is basically this one here is basically how many cats did this model predict correctly as cat? Then the denominator is going to be how many things did this model call cats, regardless of whether they are cats or not. That is precision. Then the third matrix is recall. Recall. And the formula for recall is true positives all over actual, let's say all actual positives. So the recall of cat is going to be how many cats did the model get correctly as being a cat all over how many actual cats do we have in uh, our data set inside that prediction. And when you look at this value, when you look at these metrics, you actually get a true picture, like a true picture of what is happening inside the model prediction, which is going to tell you the true power of the model. Then you now have the fourth one, which is F1 score. F1 score, which is the harmonic mean of precision and recall. Now, and that is actually what I like to use, and I've seen a lot of people use as the true measure of accuracy. So let's go code that in here. Now, to have a good idea of precision and recall, what I like to bring up is something called the confusion matrix. So let me show you that. To do that, let's firstly come up here and install the things that we need. I can say from sklearn dot metrics import confusion matrix. Let's import classification report. Yeah, I think those two are fine. Okay, we need to import let's import cborn as SNS. You import matplotlib dot pyplot as plt. So we can come here, and the first thing we're going to try to get is we're going to try to get the confusion matrix. So we're going to say train underscore conf, that is the confusion matrix of the training set. That's going to be confusion matrix. That's going to be y train. The first thing that goes in is y train, comma train breadth. Second one is going to be test confusion matrix of the test set, confusion matrix y test breadth. Excuse me. And if we print out these two, let's print out one of them so that you see. I can see that it is this particular matrix that tells us uh, a thing, and I'm going to explain what this means. But before we do that, let's actually bring up the chart properly. So we're going to come to this place and say, let's use subplot. So I can say plt dot subplot, and I'm sorry, start off with fig, comma axis equals plt dot subplot, and we're going to say n rows, number of rows equals 1, number of columns is going to be equals to 2, because it's going to be 1 by 2, one line. Then we're going to say fixed size equals, that's going to be tuple 20 comma maybe 5, I guess. Then we can run that and even see how it comes out. That is the yeah, this is not bad. This is not bad. So the only thing we just need to do is to, I don't think, do we need to put it on just that SNS does set underscore style, just to style it a little bit. So that's going to be dark grid, something like dark grid will suffice. So if we run that, so let's put our chart on this. So we can go here and say SNS, excuse me, SNS dot heat map, and data is going to be equals to train conf, and our axis is going to be axis 0. If we run that, now we have this confusion matrix here, but we want to actually remove this bar here and put the value of the matrix on the chart. So we are going to say a note to annotate. We're going to say true. We're going to say c bar equals false. Let's run that. Oh, yeah, we want it to actually write the whole number, not do this standard form thing. So we're going to say FMT equals D. Yeah, so we see that in the train set, you get 167, 3, 1, 284. I'm going to explain what that means shortly. So if I should highlight this and get for the test set also, I will come here, excuse me, I will do Control D. No, just one alone. Test confusion. We should change this to 1. Great. So now we see 40 and 2 here. Now let's try and interpret this. So on the y-axis here, like on this line here, is your prediction. And on this axis here is your actual. So here's what I mean. I can come here and say axis 0 dot set underscore x label. And that's going to be actual. Then I can copy that and paste it again and say axis 1. No, axis 0 also. So that's going to be set y label. So if we run that now, no, the other one is going to be predicted. So y label is going to be prediction. Prediction. Now, so on this end here, on this side is the model prediction, on this side is the actual. So what does that mean? It means the model predicted 160, got 167 prediction of 0 correctly. That is 167 data entry record are 0 that the model actually predicted as 0. Then 3 are actual zeros that the model predicted as 1. Then 1, just 1 is actual 1, actual 0 that the model predicted as 1. Then we have 284 ones that the model correctly predicted as 1, right? And this value here, we call this one true positive, false positives, false negatives, true negatives. Now, how do we now get, and the same thing for the test also. So how do we now get precision and recall? So precision, like I showed you earlier, is true positive all over all positive predictions. So yeah, that's going to be true positive 167 divided by 167 plus 1, which is 168. So if I should come in, let me do this first and copy. Where's my train conf and test conf? Oh, yeah, right. So I can copy this and Control Z, 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 Control C. So I should come to this place and paste this. And now I'm not just going to be using this anymore. I'm going to remove it. Remove this also. So I'm going to be getting classification report. I'm going to be getting classification report here. So what I'm going to do is Control D this and say classification report like this. So I'm going to be printing print f string train report, and we can put that in curly braces and end that also and end this bracket, and I can do this, then add this line break here and just copy this whole one, paste it here, and this is going to be for test. So I can Control D this Now, if I should run this, that's going to bring out our report. So for training report, we see that precision is 0.99, recall is 0.98 for class 0, and F1 score is 0.99. So how did it came about this 0.99 as being the precision? That is 167 divided by 167 over 168. How did you come about this 0.98 for recall? 167 divided by 167 all over 170. That is this all over this plus this. Then for class 1, how did you get 0.99? That is 284 divided by 284 plus 3. And the other one is, yes, that's for precision. Then precision of 1, that's going to be, precision of 1 is 284 divided by 284 plus 3. Yes, and the recall of 1 is going to be 284 divided by 285, which is almost 1, like 0.9999, something like that. Then lastly, let us see. Yeah, perfect. So lastly, what we now want to see is, okay, how did it come about the F1 score? So the F1 score is the harmonic mean of the precision and the recall. And this is how we actually check and 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 properly evaluate our model. So it means that I usually just use F1 score. So what this means is that the model is actually performing for, but just slightly, by point 1, by 0.01 units, the model is performing better on the train set than it is on the test set. You wouldn't call this overfitting really, because it's really, really small, really, really small. So this is the way you evaluate a classification problem, by using confusion matrix, precision recall, and F1 score. And that is just the general idea. What we've looked at is the general idea behind logistic regression. And we've also seen how to evaluate classification problems. And really, precision recall, confusion matrix, all of that stuff, they are not only used for logistic regression, they are generally used for every single um, classification algorithm, classification problem that you can think of. They are always good enough. So that is that on logistic regression. Majority of the ideas that we've shared in this one, we're going to be retouching on them over and over and over again in the subsequent algorithms that we're going to be um, checking, that we're going to be going through together. So that is that. See you in the next one.